Hi, I'm John Enright, Principal Engineer at Amazon Robotics. Today, I'll talk about what I call precision autonomy. At Amazon Robotics, we make the drive units that store, move, and sort Amazon inventory and customer orders throughout the fulfillment network. We're best known for our high-density grid-based systems. These systems rely on centralized planners that have full awareness of all dynamic agents in the dedicated space. Today, I'm talking about a new kind of system that works in shared human-robot collaborative spaces. This gives us greater flexibility to apply automation and autonomy to critical areas of the fulfillment network. Meet Proteus, our new autonomous mobile robot. Our design focuses on safety, efficiency, and cost-effectiveness. We employ a wide range of diverse and redundant sensing modalities that allow us to provide certain guarantees on vehicle behavior. It also gives us a breadth of tools to apply to perception techniques, as we'll talk about soon. Because we operate in a shared collaborative space, we have to adapt to unexpected changes in the environment, and we have to ensure to work hard to design our vehicle so that it's easy to work with. Today, we'll talk about developing this vehicle and its new capabilities and challenges we face along the way. Our business goal is to store, move, and sort these blue go-karts, as they're called, which are ubiquitous in the Amazon network. First, we have to define the problem of handling payloads in a collaborative environment with people. Next, we face supply chain challenges. We'll talk about how we got scrappy and worked around it. Last, we'll dig into details of some of the perception techniques we employ for the robot to do its job. At a conceptual level, what does it mean for the autonomous vehicle to move payloads in a collaborative environment with people? On the one hand, it certainly means that humans or other agents may inject what appears to be unexpected change to the environment, and we have to react to it. For example, a person might place a go-kart in a place we don't expect, or they might place it imprecisely from the vehicle's perspective. On the other hand, there's a large gray area between that kind of framing and autonomous system that has to enter an environment with no priors and has to figure out an appropriate cart to move and where to move it. So fortunately, a colleague of mine wrote up an explicit conceptual framework to think through these options. On one end, you've got unstructured inferred availability. This is where the vehicle has to literally search the warehouse for an appropriate payload to move. On the other end, you've got semi-structured single cart staging. Now this framing means that go-karts generally have known locations. Location updates are communicated via barcode scan, and the overall state of the warehouse is maintained via service layer and databases. Now, even in this more narrowly scoped problem, we still can't assume that payloads are stored so precisely that a vehicle could couple with them by pure dead reckoning. Instead, we're going to need to sense the local state of the world and close the loop. So now that we've defined the problem, let's apply the Feynman method and write down the answer. If we can write down the steps, even in an oversimplified manner, we're halfway there. The service layer will tell the autonomous system which go-kart to pick up in its current location. The vehicle's job is to drive across the building, pick up the cart, drive across the building again, put the cart down. Simple so far. Let's drill down to the next layer. When we arrive at our destination location, first of all, our global localization and navigation systems need to get us in the correct vicinity. Next, the cart needs to be in its expected location. If it's not, we're going to need to raise a flag to the service layer, report a virtual physical mismatch, possibly call for human help or intervention. That's how we pop up the stack when we run into that kind of problem at the global level. Assuming that all goes well, now let's break down the next set of processes into further steps. The vehicle will do a two-step detection and motion process, whereby first it will do a small S-curve to remove any lateral error, and then a more or less straight motion to tunnel and lift. Like a lot of teams these days, we ran into supply chain challenges. So we didn't have the new Proteus hardware to experiment with. How could we develop its new capabilities? We bootstrapped by creating what I call hardware approximations. We took a predecessor vehicle and we retrofit the new sensors on it. We created what we call a Proteus skateboard. This is just a hunk of metal on casters with some 3D printed parts to hold the new production sensors in exact production orientation and location. This means that if you plug your laptop in and push this thing around, you can record raw sensor data just as the future vehicle will see it. Next, we also have to adapt our environment at times, although we try to do so minimally. So for example, the predecessor vehicle could not fit under this go-kart. we had to artificially raise it. This allows us to practice the precision motion of tunneling underneath. Next, we'll talk about this new Fiducial Plus, which is a custom-made ground target which allows us to detect storage cells and do precision alignment. Lastly, I'll just mention that when we're working in this space, whenever perception is critical path, which is often the case, we start with recording raw sensor data. And then you can go back to your desk and develop our algorithms against it. Let's dig into go-kart detection. The vehicle will arrive from general navigation across the building using its navigation and localization software components. It now faces the go-kart. We're going to use a high-precision LiDAR to detect the go-kart itself as the target. If it's not exactly where it's supposed to be, we want to go to where it is, so we don't need any other anchors to orient ourselves. So we use this high-precision LiDAR to perform certain kinds of clustering and geometric matching on the go-kart itself. This gets us this nice rectangular estimate you see on the right-hand side of its current position and orientation. From that, we can perform precise tunneling motion. Next, let's talk about storage cell detection. Now, Proteus is carrying the go-kart and it arrives at a desired storage location. Initially, we thought we'll use the existing, what we call a 5S tape that outlines the storage cell to detect it. But when we went to record sensor data at a local facility, we saw that the camera angle has very low incidence with the ground floor. You have a lot of foreshortening, a lot of glare, and so generally it wasn't the right target for us. We designed instead this Fiducial Plus. It's the same precision fiducials that we know and love from our grid-based systems, wrapped with a larger green square which is visible from the front camera. So now it has a nice characteristic length. It's large enough that we can understand its position and orientation, but it's not so large that it's out of frame, even if we're off a little bit on our arrival. So now you can see on the right-hand side, we have a nice one-to-one mapping from the camera plane down to the ground plane. We use the camera's intrinsics and extrinsics calibrated in order to get that transform. This means we can apply a plethora of computer vision techniques, segmentation, geometry detection to understand this Fiducial Plus's estimate on the ground plane world, in the physical world, and then we complete the storage mission. So let's put it all together with Proteus. On the right-hand side, you'll see the vehicle detecting with its front camera the Fiducial Plus to perform an alignment and then store the go-kart precisely. On the left-hand side, you'll see the vehicle using its LiDAR to detect the go-kart itself, perform an alignment, and then tunnel underneath for the lift. In both cases, you see the two-step alignment process, and in both cases, some final millimeter adjustments are performed with upward and downward-facing cameras that can see precision barcodes. So, what did we accomplish today? Well, in retrospect, what we did was made a transition from our global localization and mapping system, which has about 1 meter to say 1/2 meter of accuracy throughout the entire building, down to our existing precision fiducials, which work on a millimeter level. Now, how do we do that? We had to bridge this gap of orders of magnitude of accuracy. And to do that, we employed local perception techniques to detect the go-kart itself or to detect the Fiducial Plus, and that works in, say, the centimeter to 5 centimeter range. So why is this important? Why is it valuable? 2 reasons really stand out from a solution perspective. One is autonomy and speed. We want full end-to-end autonomy when it comes to interacting with our payload and our endpoints. We don't want to have any delays injected into the system waiting on other steps in the process. The other one is that in the warehouse business, there's an expression, cube is king. That means that every square foot of concrete matters and has high value. And so when you go to deliver your payload and store your inventory, you must do it with high spatial density. And to do that, you need precision. The other thing you get out of this kind of system is a nice architectural decomposition so that each one of these, global localization, local perception, and precision fiducials, are their own closed loop. They use their own kind of measurements, which work on different scales and orders of magnitude, and they're their own problems. And so you can work on them independently and perfect them. Even a different set of engineers can work on perfecting them and using their own techniques over time. This year, it's all about scale and robustness. Here's a montage of footage from alpha deployments and some from dedicated testing facilities. We're working on really interesting problems related to not just making Proteus high reliability, but the entire Proteus team and vehicles working with high reliability. That means very interesting problems in the path planning, coordination, and traffic flow space. So if you like working on problems like these and products like these that can have high real-world impact, then check out careers at Amazon Robotics. clicking the link below. Thanks for watching today.